Alright, so this video we're going to be focusing on periodic trends. So anytime that we talk about periodic trends, I really want you to think about Coulomb's law, which is College Board's new obsession. So remember, Coulomb's law deals with two charged particles or two charged objects. And basically what this law says is that the force of attraction or the force of repulsion is impacted by two things. It's impacted by the magnitude of the charge, so how big is the charge of the two objects, and then also how far are the charges from each other. So when we talk about periodic trends, we're talking about things like ionization energy, atomic radius, so how large the atom is. And these properties are impacted by Coulomb's law, but in terms of the atom, it's going to be impacted by the nuclear charge. So how many protons does the atom have? So how many protons impacts how attracted the electrons are to the nucleus. The distance that the electrons are from the nuclear charge. And then also something called shielding. So shielding is the electron-electron repulsions that the valence electrons experience from the inner electrons. So we have our different energy levels. So here's our nucleus, different energy levels. Well, all the electrons on the outside will experience these repulsions from the inside energy levels, and basically that pushes the electrons a little bit further away. All right, so atomic radius. The atomic radius is how large the atom is. Now, what the trend that we will see is that the atom will get larger as we go to the left of the periodic table and also down the periodic table. So why does that happen? Well, as your nuclear charge increases, and the nuclear charge will increase as you go to the right. So as you go to the right of the periodic table, you're going to have more of a force of attraction between the valence electrons and the nucleus. So that actually pulls the electrons in a little bit closer, so that makes the size of the atom smaller. So shielding will not increase. So as we're moving in this direction on the periodic table, the number of protons increases. Shielding does not increase because we're not adding another energy level. So as we're going to the right, we're increasing our number of protons, so that means the size will decrease going to the right. So it increases going to the left. So as I go top to the bottom, so as I go down the periodic table, your size will also increase. That's because even though you're increasing your number of protons here, you're also increasing shielding. So your electron-electron repulsions increase. And also, as you go out to the outside energy levels, the distance that the electrons are away, the distance that the valence electrons are from the nucleus will also increase a little bit too. All right, so when we remove and add electrons, the size also changes. So cations are smaller. We remove electrons and then they become positively charged, or cations. Anions will be larger, and then that's because we're adding electrons to it. So we're adding more electron-electron repulsions. All right, so if I look at the calcium atom, it has 20 protons, it has 20 electrons, but the calcium ion has a +2 charge. Well, it still has 20 protons, but now it has 18 electrons. So it decreases in size. Now anions, so if I look at the chlorine atom has 17 protons, it has 17 electrons, but the chlorine ion will have a -1, so it still has 17 protons, but now it has 18 electrons, so it becomes larger. So this is kind of intuitive right here. If you lose, you get smaller. If you gain, you get bigger. So let's compare the size of iron and iron with a +2 and iron with a +3. Well, we know that the parent ion will be larger here. So iron will be greater than that of iron with a +2 because the +2, they've only lost 2 electrons, which will be larger than iron that has lost 3 electrons. Then if we compare bromine with Br minus, well, Br minus has an extra electron, so it will be smaller than Br minus. So isoelectronic ion. So when we're not just necessarily comparing the parent ion to the cation or the anion. Isoelectronic, remember, has the same electron configuration. So if you remove or add electrons, you can have the same configuration and the same number of electrons. The number of protons doesn't change, though, if you change the configuration. So let's compare the size of sodium with a positive 1, magnesium with a positive 2, and then aluminum with a positive 3. Well, let's look. Sodium with a positive 1. Well, sodium's normal configuration is 1s2, 2s2, 2p6, 3s1. Well, with a plus 1, we're going to remove that 1 electron, so that's the configuration. For magnesium with a positive 2, well, magnesium's configuration is 1s2, 2s2, 2p6, and then 3s2. Well, when it has a positive 2 charge, we lose those last 2 electrons. They have the same configuration here. Same thing for aluminum. Its configuration is this. It loses 3 electrons, so it loses these 3 right here. So they all have the same configuration. They have the same configuration, but they have a different number of protons. So remember, if you have more protons, you're going to pull those electrons in closer because the electrons are more attracted to the nucleus. So aluminum has the ability, with a positive 3 charge, has the ability to pull the electrons in closer, which makes it smaller than magnesium with a positive 2, and then sodium with a positive 1. So they all have the same number of electrons, but the number of protons is different, which means that if it has more protons, it's going to be able to pull those electrons in tighter and make it smaller. So let's do the same thing. Let's do anions this time. So phosphorus with a -3, sulfur with a -2, and then chlorine with a -3. They all have the same electron configuration when they become ions. So they all have 18 electrons at this point. But phosphorus only has 15 protons, while sulfur has 16 protons, and chlorine has 17. Well, chlorine has more protons than the other two, so if they have the same number of electrons, it's able to pull the electrons in closer. So it is smaller than sulfur with a -2, because remember it has 16 protons, and then it is also smaller than phosphorus with a positive 3 or -3. So that's how the size would work here. So basically, if you have a more negative charge here, that's going to make your size larger. If you have a more positive charge here, that's going to make it smaller. All right, so now we're going to compare all sorts of protons. We're going to compare +1, -1, -3, +2, and then -2. Now, if I go and look at the configuration, they all have 18 electrons. They all have 18 electrons, but they have different numbers of protons. So potassium has 19, chlorine has 17, phosphorus is 15, calcium is 20, and then sulfur is 16. So they all have the same number of electrons. Remember, if you have more protons, you're able to pull those electrons in tighter, so that makes it smaller. So calcium with +2 is the smallest. Then potassium with +1. Then we have 17. So chlorine with a -1, sulfur with a -2, and then finally we have phosphorus with a -3. So you'll see the more positively charged it is here, it's going to be smaller. The more negatively charged, it's going to be larger. All right, so the ionization energy trend. Well, we've already kind of talked about this. So as you move from left to right in the periodic table, the ionization energy increases. This is because nuclear charge increases. So if the nuclear charge increases but shielding does not, it means that those electrons are more attracted to the nucleus. It is harder and requires more energy to remove those electrons. Now, as I move from the bottom to the top, ionization energy increases, and that's because shielding will increase as I go in the opposite direction. So the force of attraction is less. All right, so there are two discrepancies in the ionization energy trend. So when we move from beryllium to boron, well, if I go from left to right, I should see an increase in ionization energy. However, I don't. I actually see a drop, a small drop. So that's because beryllium has the configuration of this, 1s2, 2s2, and then boron has this, 1s2, 2s2, and then 2p1. Well, when we remove an electron, we're going to move the highest energy level. Technically, we have 3 electrons in the highest energy level, but we're going to move it from the p first because the p is just a little bit further away from the nucleus than the s. So right here, we're going to remove it from the s. So it's a little bit easier to remove this one electron in this case. So you will see that trend in 3a. So you'll see that discrepancy in the trend in 3a. So explain why there's also discrepancy from nitrogen to oxygen. Well, from nitrogen to oxygen, we're again moving from left to right, so it should go up, but there's a small decrease. Well, when we look at the configuration, nitrogens is 1s2, 2s2, 2p3. Oxygen is this, 1s2, 2s2, 2p4. So remember what I said, anytime we have a discrepancy, look at the configurations. So for this, we have the electrons unpaired, completely unpaired. Here we have one pairing. Well, for that one pairing, it's easy to remove that. It's a little bit easier to remove that one electron because of that extra repulsion right there. All right, so electron affinity is basically the opposite of ionization energy. That's when we add an electron to an element in its gaseous state. That is also important. If they ask you to ever write an equation with that, it has to be in the gaseous state. So it's measured in kilojoules per mole. Remember, if it has a -1 like that, that means per, or that it's on the bottom of a fraction. So when we add an electron to the gaseous state atom, it's an exothermic process, which means it releases energy. However, the whole process where you have to make it a gas and then add that electron is endothermic. So you're going to release energy anytime you put two things together that are attracted to each other. However, if you're making something into a gas, that's going to require energy. So the electron affinity increases up and to the right for the most part. Down the group, the trend's not always as clear. So it depends. But in general, you're going to see that it increases up and to the right, just like ionization energy. All right, so electronegativity is the ability of an atom to attract electrons to itself within a covalent bond. So this only applies for when atoms are bonding together. So as I go from left to right, the electronegativity increases. So it's going to increase actually in the same direction that ionization energy increases. So up and to the right. So pretty much all the trends will go up and to the right except for radius, it's the opposite. Okay, so the exception here is going to be the noble gases because the noble gases don't typically bond. So the reason that this happens is nuclear charge is increasing, shielding does not, which means that the electrons are able to get closer to the nucleus and are able to be pulled in more within that bond. So if you have two atoms that are bonding, let's say that this one is more electronegative it's able to pull the electrons that are being shared more towards it. So it's just pulling the electrons towards itself in that bond. So there's almost an unequal distribution of electrons. So as I go from the bottom to the top, I'm going to see an increase, and that's because shielding increases as you go in the opposite direction. So those electrons are not able to feel the pull of the other nucleus in that bond.